example, just for simplicity. Legally exhaustive regressors, well-behaved, so no specific problems here with our estimation principle, and for as a starting point we use here almost elastic and residual calculations also no problem. So we have diagonal covariance matrix of the residual, so this is just for simplicity. Okay. So what we saw when you look at these GMMs, these method moments, and these square principles, what you should notice is that those two estimation principles do not really require any distribution of assumptions about the errors. So think, for example, look for example at the least square principle. For some, just for simplicity, in order to derive the standard error and the distribution of the error, we had made some assumptions about normality of the residuals. Well, but we also showed that, in principle, you can derive from the square estimator whatever the distribution of the errors is. Right? You don't need normality to derive from the square estimator. And very similar to the GMM methods. So this is why you call these estimation strategies sometimes distribution-free methods. Very different with the maximum likelihood procedure. Here, by contrast, we make the assumption that we exactly know the distribution of the errors. For example, that it's normally distributed. But this method is not restricted to know normal distributions. Okay, so we do not only talk about the average or the covariance that has to be 0 between regressors and the error. So we do not talk about only the first and second moments of these random variables, but we assume that we know everything about distribution. So all moments, skewness, kurtosis, whatever you want, any correlation with it, because we know how these are distributed here for given x. So you see that maximum likelihood has more explicit assumptions. So we have to know more about the distribution of the errors when we apply maximum likelihood estimation than when we just take the square principle, for example. But as always, if you invest more, if you make more assumptions about the residuals, then there are also some, this is the cost, so to say, right? But there is also some benefit. If I assume that I know everything about distribution, not only some covariances or expected values or something like that, like here, then of course, it's not surprising that if this is all true, then the estimator that is derived from these more general assumptions are extremely good. Right? So one can show that if you apply maximum likelihood estimation, that these are usually efficient and asymptotically normal. Right? So very nice assumption. So in a way, if it's okay to assume that I know the distribution, so if this is okay, then you can't do better than maximum likelihood estimation. We already had some efficiency results for these squared, right? So you see that already suggests that there must be some cases where maximum likelihood estimation, which is asymptotically efficient, here somehow coincides with least square estimation, which is efficient according to Lars Marcus, right? Okay. So after talking about the general properties of maximum likelihood estimation and what is the principle of maximum estimation, we will also talk about some general testing principles, testing ideas that are built on the maximum likelihood estimation. Good. Okay. So let me start talking about very general about the maximum likelihood estimation principle. So what is the idea of maximum likelihood estimation? And the starting point here is a very simple example. It's a wheel of fortune game, right? Glücksrad, maybe in German, right? In German. So look here. You have two wheels, and the idea is, you spin that wheel, right? And whenever it stops here in the blue, here above in the blue area, then one probability of winning is 1 over 4. Right? Okay. There's the second wheel, B, and you see here the blue area is much wider, and according to the probability of winning here, that wheel B is 3 over 4. Okay? And now suppose you don't know, and now suppose you don't know which kind of wheel you're confronted with. Right? You're participating in that lottery, spinning a wheel, but you don't know is it wheel A or wheel B. So the unknown parameter here is obviously the probability of winning. Right? And here are just two cases, right? Either 1 over 4 or 3 over 4. Okay? You see that this is a very similar situation which we are in applied practice, in applied economics, right? There are these unknown parameters beta we want to estimate, we just don't know, right? And here, well, there are just two possibilities to begin with. 1 over 4, 3 over 4. Well, and what would you do in applied economics if you have unknown parameters, right, which you want to learn about? Well, you collect data, and then we estimate the parameters. Same here. Well, we collect data. What does it mean? Well, we just spin the wheel and look whether we won or not. And then we try to conclude from the outcome which of the wheels are more likely. Well, so here the assumption is that we spun the wheels 3 times. Well, and the outcome is win-win loss. And now the question is, well, no, this is the data we have, right? And now the question is how to conclude from that outcome optimally whether we have wheel A or wheel B. Right? Okay, so question, given that outcome, which kind of wheel was spun? Well, the idea is, of course, that you, just to calculate somehow the probabilities, right, of these outcomes, right? So what is the probability to observe the sequence that we observed, right? And that, of course, depends on the kind of the wheel, right? So if we have wheel A, the probability of winning is 1 over 4, then the probability of observing win-win loss, so observing the actual outcome in the data we have, is obviously 1 over 4 times 1 over 4 times 3 over 4, blah, 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 less than 5%. Okay? Yeah? Okay. Wheel B, same idea. Well, then, now, if this is actually the result of wheel B, then the probability of observing exactly that outcome is 3 over 4 times 3 over 4 times 1 over 4, blah, 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 is 40%. And now you see the maximum likelihood principle. The maximum likelihood principle says, choose as your estimator, as your maximum likelihood estimator of the unknown parameter P, that value that maximizes the probability of the observed outcome. Okay? This is the idea, the very natural, plausible idea of maximum likelihood estimation. So you observe this, what is the parameter, what is the value of your unknown parameter that makes this outcome the most likely? Okay, so obviously, for example, you would never choose P0, right? Because, if the probability of winning is 0, then you will never observe something like win-win loss, because it's just impossible to win, right?
Does that mean we always know the P value that is in question? Like, do we always know we compare?
No, this one, no, not always. This is just this example,
Okay.
right? So here we just assume there are only 2 possibilities, this or that. Now you observe win-win loss. What would your decision, right? Of course, this can be generalized, right? Why should we know that it's 1 over 4 and 3 over 4, right? Let's go up one step further and say we have no clue. It's just P, right? And now again, there's some there's just one wheel of fortune with some unknown probability p, well, so this blue area can be everything, right? And now the question is, well, we do just exactly the same. We spun the wheel, we observe win-win loss of that unknown wheel of fortune, and now we apply the maximum likelihood principle again, right? So we calculate the probability of having observed exactly that outcome. Win-win loss. Well, this probability of winning is now this unknown p, that is obviously p times 1 over, or 1 minus p, or p squared minus this one. And here comes the first critical term that you should understand. This is the so-called likelihood function. Well, and that's a little bit strange at the first sight, because what we did is just we calculated probability, right? This is the probability of having observed this outcome. Why do statisticians introduce a new term, likelihood function? We never, in statistics 1, 2, or whatever, we never talk about likelihoods. Usually we talk about probabilities. Okay, yeah. So what's the difference? You see this? Let's look at this here. This is a likelihood function. It is a function of p, obviously. And this is a likelihood, depending on p, given that outcome. So obviously, if the outcome would be different, if the outcome would be win-win-win, then we would have here p over 3, right? So the value of the likelihood function depends here not on the observed outcome. And that's the difference between the likelihood of something and the probability of something. If we talk in statistics about the probability of something, then the perspective is we know the distribution, so we know p, and we ask, given p, how likely is some outcome, right? In the likelihood, it's just the other way around. It's not that we know what p is and we calculate the probability of an outcome, whatever the outcome is, right? The perspective is the other way around. We don't know p, right? But we know the outcome. So it's not given p, what is the probability of something? It's given the outcome, what is the likelihood of that? Right? Okay. So the conceptual difference between a probability and the likelihood is that in the likelihood, p is the unknown parameter, and this is given. And if we talk about the probability of something, it's just the other way around. P is given, and we ask, what is win-win, what's the probability of win-win loss? This conceptual difference is important to understand because the numbers that come out looks exactly the same, right? So the value of the likelihood for a given outcome is of course nothing but the probability of having observed that outcome depending on p. Okay? But this is think about that, right? This is the conceptual difference between probability. I know p, just give me some outcome and I give you the probability of that outcome because I know p. This is the probability. But now we don't know p, but we know the outcome, and we just put it another way around and calculate the probabilities or the likelihood, right, of that outcome depending on p. Okay? So this is called the likelihood function. So it's a probability somehow, right, that depends on unknown parameters. And now, of course, applying this idea, the maximum likelihood principle, in this more general concept is, well, given the observed sequence, given our data we observe, what parameter, vector, or here just p, maximizes the likelihood? Right? You see, this is exactly the same idea as here. Here we have just two values, right? Is p this or that? So a very restricted set of choice, right? And here we are more general and ask, well, what can be p? So the likelihood function in that specific example is just this. So if you would plot it, it would look like this. This is p square minus p to the power of 3, right? Yeah, well, and the maximum likelihood principle tells you, well, okay, for given this likelihood, choose that p that maximizes the likelihood. And of course, we know how to maximize such a function. Take the first order. Here, first order condition, takes the first derivative, put it to 0, solve for p. It is, not surprisingly, I would say 2 over 3. See that? If I have 2 wins and 1 loss, probability of winning, well, the most likely value is 2 over 3. Okay? Of course, it could be a different one, right? You see, also if p is smaller or larger than 2 over 3, it could happen that I observe win-win-loss. Yeah, why not? Right? But this outcome is less likely. And the maximum likelihood estimator says, well, choose that one, choose that parameter value, which maximizes the likelihood. So that, because this guarantees that what you observe is the most likely outcome. Okay, so here p star would be the maximum likely estimator of p. So, if you look at that likelihood function, you may already have some feeling, look here we have an estimator. It is, of course, a random variable because it depends on a random outcome, win-win-loss, right? So we are used to that. So it's a random variable. It will have a standard error, a variance, estimation uncertainty. So and if you now look at its likelihood function here, you should already see, well, what could be the drivers of estimation uncertainty in a maximum likelihood estimator. Okay. So the likelihood function here looks like, this, okay? And now suppose the likelihood function would be like that. So same p star, okay? Which likelihood would you prefer? Black one or the red one? Yeah. Okay, same maximum.
Black one.
Black one, why?
I mean, as there's like a smaller variance, it's more precise.
Yes. Yeah, look. If we talk about estimation uncertainty, it is a question, well, okay, the point estimate is this one, suppose, right? But could it be like this? Could it be that? And you see, if the likelihood function is more steep, then if you go away a little bit from p star, right? So if you ask, okay, I estimated 2 over 3 is the maximum likelihood estimated, but could it be 0.7 or 0.8 or a little bit smaller or so, How sure can you be that it's really 2 over 3 and not, I don't know, 2 over 4, right? Then you see, if you have a very steep likelihood, then if you go a little bit away from your optimal value, the likelihood goes down dramatically. However, if the likelihood is more flat, look at the extreme case. suppose it's like that. This is a maximum, right? Then, you know, yeah, okay, the maximum is now P star, great. But actually, if it would be a little bit smaller or a little bit higher, the likelihood is more or less exactly the same, right? So if the likelihood function would be like that, then it would be much harder for us to differentiate between P star and a value of, and an estimate that is a little bit smaller or a little bit higher. Because likelihood is more or less identical. What that figure already suggests is that for the estimation uncertainty, for the variance of the maximum likelihood estimator, the second derivative of the likelihood function is key. Right? Here, extreme second derivative. Here, second derivative more or less 0. Okay? So the higher the curvature, the better for maximum likelihood estimation, because it makes it easier to differentiate between different values. Okay, look here. You can go even further, of course, right? So that's taking an example, you know, and you see how general this maximum likelihood principle is. It's not only possible, you know, to say P low or P high or P somewhere between 0 and 1. You can, of course, also say, well, let's have not only 3 data points, but any data points. Like in economic practice, you know, we don't make econometric with 3 observations usually, yeah? So that's n times. Well, and what you observe is, if you spun the wheel n times, you observe k time winning and n minus k not winning. What is the likelihood function of that? Well, that's simple, right? Easy. Likelihood function of exactly that outcome. Well, you win k times and you lose that one. Okay, so next step would be, well, the idea of maximum likelihood estimation is now again, right? Okay, choose now P that the likelihood of the observed outcome is maximized. Okay, so now you could do the first derivative of the likelihood function, set it to 0, solve for P. Right? Of course, in principle you could do exactly the same as here, but now a little bit more complicated. Okay, so in many applications the likelihood functions look really complicated, much more complicated than in this easy example. Right? If you have 1,000 observations, right, then, and it's not binomial distributed, but we talk about residual errors which are somehow distributed, then you can imagine likelihood functions are not so easy to maximize, right? So, therefore, it is a great relief that in many applications we can simplify the likelihood functions by just taking the logs. So this means taking the natural log, logarithmus naturalis of that one. You can do that because this is always a positive number, right? So this is well defined, and you see, you know, that in that case, taking the logs here simplifies this likelihood here dramatically to that one here. Logs makes takes the exponent here, you know, and now it's much easier to solve for the optimal P, right? Because if you now take the first derivative of that, then you see, well, you know, this is k times 1 over P plus n minus k, blah, 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 blah. Putting it to 0, you can solve this. The optimal P is k over n. Again, right, the very expected outcome, right? If I spun n times and I observe k winnings, then the best guess for the probability of winning is k over n. It's like 2 over 3 or 1 over 4, whatever happens here. Very specific example. Okay? There's one thing why is that possible? So look here, we want to maximize the likelihood function. We want to find the p that maximizes L of p. And now I just said, oh come on, let's take the log of it. And now I maximize the log of the likelihood function. Why does that lead to the apparently correct result? I want to maximize this. Why is it okay to say, oh come on, I take the log and I maximize that? Why does it always lead to the same parameter estimate? You know that? So suppose I would take just I don't know, the cosine of it or something, some arbitrary function of L and P. Would that also give me the same maximum value? Yeah.
I would say it's like issue of technique because that it looks a little bit complicated, but actually they are same, and so that.
Yeah, but you know why is it allowed? So if I would just take a general function, some function, that would be wrong.
It could be that they will align with the original concept and principle.
No. What are, obviously, it is a particular property of the logarithm that allows me that, right? Because if I take just an arbitrary function, that would be wrong. I want to maximize this function. I cannot just manipulate that function and can be trustful that the result of taking first order would give me exactly the correct value, right? Obviously, that's not always true. You want to maximize this function, not that, right? How can that be okay? What are the property of the logarithm that allows me, makes me that? It is the monotonicity of that. Right?
Argumentation, like aggregated function about to aggregate some.
It is the monotonicity of that function that allows me to do that.
Okay.
You might have seen that, or should have seen that very often in macroeconomics or in microeconomics, right? Where some utility function or production function, whatever, is, for example, from the conductive type, right? And what do you do in order to maximize it? You take the log of it. And no surprise, surprise, it gives you exactly the correct cost minimizing or utility maximizing or whatever solution, right? So if you have a function you want to maximize, and if you take a monotonic transformation of that function, so you change the function, but you do not change the order of the values, then the maximum here stays the same. All right? Okay. So this is why people applying the maximum likelihood estimation, typically consider the so-called log likelihood function. So they consider the log likelihood function. Okay? So not be surprised. So why is it okay to evaluate the maximum likelihood principle with the log likelihood function, because the log doesn't change the maximum here. All right. Okay. So here is the. So now you should have understood the maximum likelihood principle. What is the likelihood function? What is the difference between the likelihood function and the probability, right? And why can I maximize the likelihood function just by using the log likelihood? Okay, so in this example, it was maybe, I don't know whether it was so convincing that it simplifies everything, but now look at our general regression framework. So now we have here these errors, right? Or some random variable which is normally distributed, right? With some expected value and covariance. And, well, look, we assume that we know everything about the distribution, right? So we know it's normally distributed, for example, here. So look, this is how the normally distributed, the density function of the normal distribution look like, right? For these unknown parameters, mu, the expected value, and the sigma square. These are the two unknown parameters here. This is just the density of the normal distribution, right? So for given mu and for given sigma square, right? And the UI, these are our observations. These are the data we observe for u. Okay? So for UI, given mu and sigma squared is just this. So what is the likelihood function? The likelihood function is now here just for all our data we observed, right? So we have n observations for that random variable. N. What is the joint probability of observing this vector u1, u2, u3, u4 power of n? It is a product of all the densities, right? Because we assume that the observations ui are independent. Okay? So it's exactly like here, right? Win, what is the probability of win-win? It's probability p times p, right? P times p because the wheels are independent versus spun for the wheel. The outcomes of spinning the wheel is independent of another one. So and here exactly the same. We assume that the ui are independent, and therefore the likelihood is just a product of these densities. And now you see how helpful taking the log likelihood is in practice when you have something like this. Because maximizing that likelihood function would be super difficult, right? Look on, if you just insert here, it is a product of these guys here, n times. Difficult. But, as we just discussed, you can just take the log likelihood, right? So, the log likelihood, if you apply the log to a product, it gets sum, exactly like here, right? Taking the log of that product gives the sum, which is much easier to maximize. And this is the log likelihood if you apply it to the normal distribution. Okay? And now that we have derived for that example, we have n observations for a random variable, which unknown parameter mu, expected value, and unknown variance sigma square. Now we can apply the maximum likelihood principle. So we choose theta, so the vector of unknown parameters, that maximizes the log likelihood. This is just saying this in math terms, right? So we're choosing the theta in a way such that log L is maximized. Okay, argmax is, this is a value that maximizes this. This is a maximum likelihood estimator. Okay, and again, the maximum likelihood principle says, well, given the data, given u1, u2, u3, u4, and so on, that vector here, so that maximum likelihood estimator are the most likely parameter values for our observed data. Okay, so what can be shown is that this estimator here is, if the assumptions about the distribution function were correct, the estimator is consistent and asymptotically normal and efficient, right? And of course, look here, we started with two wheels of fortune, well, and we generalized even more. Now we went from a binomial distribution, P or not, one or not, win or not win, to the normal distribution, right? Which is, as we learned, in practice, a very common assumption. But in principle, of course, you can apply that maximum likelihood estimation for any parametric probability distribution function, for any PDF, right? So if it's not normal distributed, if it's t-distributed or whatever distributed, then of course, then the distribution would be then here a t-distribution or whatever distribution. And then the likelihood function would be the product of this, and so on and so on. But you know, it would be more complicated probably, right? And in particular, if you have something like a t-distribution, right, if it's more complicated, then maybe there is no closed form solution for the estimator, though there are some numerics here involved, right? So for some application of the maximum likelihood estimator, it is not as easy as for the least-square estimator, where you just say, the least-square estimator is x prime, x blah, 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 blah. So give me your data, and this is the formula that gives me exactly in an explicit closed form solution what the parameter values are. I estimate this is not typically not the case for maximum likelihood estimating. Okay, simply because these functions are too complicated. Okay. There is, however, one special case, you know, where maximum likelihood estimation collapses to a very, you know, very well-known candidate. Well, and this is exactly the least-square estimation procedure. Look here. Let's suppose we have this linear regression model and here's standard assumption about the errors, right? So what is now the conditional? So if this is normal, then y is normal, right? Because this is a linear function upon something normally distributed. Okay, so what is the distribution of y? Given x, given our data, it is x beta, if our model is correct. This is the expected value, because expected value of this is x beta plus 0. And this is the covariance matrix here. Right? So what is then the density function of that? Well, for observation I, given xi, well, it's just because we assume normality here. This is z. This is this guy. Okay? So, and notice that this is equivalent here to ui, because we assumed that the stochastics here come directly from the hues. Right? If this here varies, that varies. So now, because they're independent, again, the likelihood function of all our n observations for y is just the product of these, of the n time product of these guys. Right? Very similar to that one here. And now we take the log, and you see this is a log likelihood function for given, for this is our regressors, this is our observed data for our dependent variable, and these are the unknown parameters, sigma square and beta, we want to estimate. Okay, so look, taking the logs, right, this is just here constant, right, taking the log, applied to exponential function, cancels out, so to say, right, log exponential are inverse to each other, so therefore you have here the log minus n over half, because we have this here n times, right? We have n observations, so the product is n times this, therefore we have n times half the log of sigma square, and here again, this is just here. If you have n observations, then you get the inner product of these residual vectors. Yeah, you see, this is just the sum of the square residuals. Okay, and again, now we derive the log likelihood function for our linear regression model under the assumption of normal residuals. The next step is choose beta and sigma, so maximize this with respect to sigma and beta in order to get the maximum likelihood estimate.
Could you repeat again why it's n over 2? And
This here?
Yes.
So if you just write down here, if you do this here for that example, right? So what we want to have is, so the data we observe is not just one observation, yi, but we observe this for y1, first observation, second, third, blah, 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 blah. what you want to have is a likelihood for all our joint data set. So what we want to have is a likelihood of observing exactly that vector of y's, right? And the likelihood for this is the product of that from 1 to n, right? And if you take now the log of that product, it's going to sum. And now it's just, step for step applying the log rules, right? We learned in Math 101. Yeah, so that the log of a product is the sum of the log and so on. Okay. So, what happens, this is a log likelihood of the linear regression model and normality. So now we take the first order conditions, right? And now it's a little bit, now it's get tedious, right? But, relax, because everything we do here is, taking the first derivative, set it to 0, and all these things, right? So, the interesting thing here is that although we have here a vector of beta and a sigma square, we don't know, so this is a multivariate optimization problem. Here in that case, one can show that you can solve this in 2 steps. So you can first estimate sigma hat here, and you see this is nothing but the sum of squared residuals divided by 1 over n. So an estimate for sigma square we more or less know from least squares estimation. And then put this estimate into the first derivative with respect to the betas. Right? And if you do this, then the log likelihood simplifies to that. And what you see is here, in the end, this is just a constant here that doesn't depend on sigma and beta. The only interesting thing here is that guy here. Well, this log of something is the, because we take here the minus sign, so this is here maximized whenever this here is minimized. And this is nothing but the sum of the squared residuals. Right? And this is why one can show that if you maximize this concentrated likelihood with respect to beta, this is exactly, this gives you exactly the least square estimate. Okay? So, maximum likelihood estimation under normality of a linear regression model is more or less nothing but applying these squares. Mm-hmm.
So I think my question is way more basic, but it's like I don't understand the step of how we got from multiplying the p's to multiplying density functions of error terms.
You mean you understand this?
Yeah.
Okay.
But
And
then
now look, this is a discrete random variable.
yes.
So I win or I don't win. 0, 1.
Mm-hmm.
In practice of economics, we have continuous random variables. Because the error could be some number, 0.3, minus 0.5. This is why we go from a binomial distribution here for that introducing example to a continuous random variable. So the random variable here is discrete. It can only take the value 0 or 1. The random variable in the applications actually we are interested in most cases, is that that our random variable u is a continuous random variable. And the probabilities, how do you calculate probabilities of a continuous random variable, of normal distribution variable, for example, right? It's not just p. There is no probability mass for a single outcome. You can only have a density function, and probabilities are the area under the density. Recall? Right? So this is not a probability. Right? Here, this is the value of the density function because we have a continuous random variable. Yeah? If u is a normally distributed variable, univariate case, what is the probability that a normally distributed variable takes the value 0, for example? What is that? You have a random variable, it's normally distributed. What is the probability that this random variable takes the value 0?
0.
Exactly. Because it's a continuous thing. You can only take, if you have a continuous random variable, you can only talk about the probability of intervals, right? And this is why the probability, this is why you calculate the probability of continuous random variable always with using a density function, and then you take the area under the curve, right? And therefore, the likelihood is not now given just a probability p, it's the value of the density function.
Okay, because the density gives us the probability.
Yeah,
but kind of.
yeah,
Okay,
yeah,
thanks.
yeah, exactly. Okay. All right. So, there's one small difference between the maximum likelihood estimator and the least square estimator. Do you see that? So the beta estimator is exactly identical. But you go to R and say, here's a linear regression model with normal errors, please estimate with least square, and then please estimate with maximum likelihood, you will get exactly numerically the same numbers. This one. But what differs? Look here. The maximum likelihood estimator for the variance is 1 over n sum of squared residuals. Remember what is the estimator for in the least square case? For sigma and sigma squared? Remember that? Always is also, of course, somewhat depends on the residual sum of squares. But you divide not by 1 over n, you divide by 1 over n minus k. And k was a number of parameters of beta. Yeah? Check your formula. Bachelor 101. Okay? So you see, and we also proved, right, that we have to choose 1 over n minus k in order to get an unbiased estimate of sigma. So this here is a biased estimate of the variance. Okay? Because an unbiased estimate, this is what we proved in the least square chapter, is not 1 over n, it's 1 over n minus k. Question, is that a big problem? Yeah?
Not if n is large.
Yeah, exactly, right? So if n is large, the difference is negligible. Okay? Therefore, this here is a biased estimate of the variance, but it is asymptotically unbiased. Right? Because if n goes to infinity, the difference between this estimate, the maximum likely estimate, and the unbiased estimate coming from least square is vanished. Okay. Okay, this is why in some textbooks you might find things that are not exactly the same or something like that. This is just, in small samples, and it only goes for sigma. All right. So look, I will not prove here that maximum likelihood is sufficient, but it's important that you get the intuition of it, right? Look here. This is if our assumption about the distribution of ui are correct, right? It is really a normal distributed variable, for example, right? And if we base our analysis on the normal distribution, then we use all the information that is relevant for our random variable. And therefore, it's not surprising that maximum likelihood estimation is efficient. Because first of all, it's an unbiased estimator, right? And second, it uses all the information that is relevant. All right. So let us go further by introducing some general concepts. Yeah. Well, when you check textbooks or when you check empirical papers, maybe every now and then, you will be confronted with some terms, which I want to introduce. But they're very straightforward. If you've got the general principle of maximum likelihood estimation, then it's clear that we have to talk about something like the first derivative of the likelihood function. Yeah, because we take the first order condition, we maximize it, okay? So, if you talk about the maximum likelihood estimator, you talk about the first derivative of it, because you want to maximize it. And therefore, it got a known in here, the score. This is just the gradient, so the vector of the first derivative of the likelihood function with respect to the unknown parameters. This is called the score function, right? And if you have k explanatory variables, and a constant and a variance, then g, for example, would be a k plus 2 vector. Yeah, because we have k plus 2 unknown parameters to estimate in that case. Well, here again is a likelihood function for the linear regression model under normality. And under normality, you take the first derivatives, well, then you get exactly these values it just used in order to derive the maximum likelihood estimation of the linear regression model that collapsed here to minimizing the least squares. Okay? But of course, that first derivatives, everything we observe, everything we estimate, and therefore also these first derivatives, they depend on our observations, right? And these are random. And therefore, of course, the score function, which is emphasized here, is also a random variable, right? Because it depends on what we observe. All right. So the second important thing, besides the score function, is it's related to the second derivative. And this is what I try to prepare here, so that you're not too surprised that we all have to talk about the second derivatives of a likelihood function, because obviously the second derivative is one that gives me something about the estimation uncertainty, about the variance of the maximum likelihood estimator. Right? And this is why we talk here about the Hessian matrix. Right? We have a multivariate function, the likelihood function depends on a set of, I don't know, how many, k plus 2 or k whatever, k unknown parameters, right? We want to maximize that log likelihood or likelihood function with respect to these k unknown parameters. Therefore, the score has to be 0, well, the gradient has to be 0, first order condition, right? But now what derives the uncertainty? This is the second derivative. The first derivative says, okay, here's 0. But the second derivative, so whether it's like this or like that tells me something about how certain I am that the maximum likelihood estimator is exactly here and not there. Okay, so this is why the second order derivatives here play a role, and exactly those second order derivatives here are relevant for the covariance matrix of our estimator. Yeah? Here you see this is the covariance matrix of the vector of unknown parameters here. So what's the deviation of our estimator from the expected value? So this should be small if the estimation uncertainty is small. And here you see if n, the number of observation goes to infinity, here it's a consistent estimate, therefore here O1 over n, this goes to 0 then. But here you have this is somehow an artificial I, where I is for information matrix. Because this matrix here, which is nothing but here the expected Hessian of a log likelihood function, so you see you can derive this as an outer product of the gradients. So, right, not the inner product, which gives you a number, but the outer product, which gives you a matrix. This here gives you something, how informative is my data set? Here. And this is here, that's just a footnote, well, and that's very special case log diagonal, meaning that there's no, that the estimation of the sigma, and this here is this here is that follows from that one, from that observation. Right? That this here does not depend on the sigma. So that's not important. Okay, so what you see is here this, not like that, then this is small, because we divide, right? All right? Okay, so second order derivatives are key for quantifying the estimation uncertainty in the maximum likelihood principle. So there are more, they are very, there are a lot of mathematical, statistical results out there about maximum likelihood estimation, right? I don't want to go into these details, but there's something you should know, So I already said that maximum likelihood estimation is asymptotically efficient. So if the assumption about your random variables are correct, then you can't do better than maximum likelihood estimation, because you use all the information that is available, right? Not only the first moment, not only the second moment, you use everything, right? So, and therefore you can show that, well, if you want to have an unbiased estimator of your parameter vector, then you can't do better than the maximum likelihood estimation. There's a very general result that shows you that there is something called a Kramer-Rao lower bound of the covariance matrix. So there is some minimum uncertainty. And exactly the covariance matrix of the maximum likelihood estimation gives you that minimum of the covariance matrix of your estimator, right? So if you have any unbiased estimator, this theorem tells you that, well, the covariance matrix is always larger than the one given here by the maximum likelihood estimation. Okay? And please recall, right, these are not numbers, right? Sometimes I talk about these as if they were numbers in order to simplify things for you, intuition and so. But we talk about this, when we talked about the Gauss-Markov theorem, for example, when the covariance larger than another one, right? Positive definiteness of matrices play a role here. Okay, but this is just technique. Okay. So let us summarize. Maximum likelihood estimation, you should have understood the general principle of it, right? So what characterizes the maximum likelihood estimator? You should have understood what a likelihood function is. Given the data, calculate the probability of having observed that one. Maximum likelihood principle is choose the parameters in order that maximize the observed data. So likelihood principle. Why do we talk in practice so often about the log likelihood? Well, because the log is a monotonic transformation, and the maximized value would be the same as for the likelihood. Very often, in particular in our econometric applications, where we have n observations and independent errors, and the likelihood is an n-dimensional product. Whoa, taking the log of it simplifies the function you want to maximize dramatically. Okay, therefore log likelihood often plays a big role. Okay, we stated that we talked a little bit about score function, and in particular about the information matrix, which is given by this outer product of the scores. And this is, I don't show that, so I have to warn you about that. It's just a statement here. This is equivalent to the expected value of the Hessian matrix. The Hessian is the matrix of the second order derivatives, right? So there's a mathematical proposition that links the score function, first order derivatives, with the second order derivatives. And it goes like this. Okay? So this is what is used here. The information matrix is based on the second order derivative. This is a picture you should have in mind. This is the intuition. course, you know, it's always a little bit fuzzy. Well, when I say, if this gets large, we divide by it, and therefore, right, but yeah, you know, of course we can divide by a matrix, you know, we have to take the inverse, it's something different, right? But the intuition, I think, is okay, right? So, if the Hessian matrix here gives you large second-order derivatives, that means it is like this and not like that, then this matrix here gets large, and therefore if you divide by a large matrix, inverse of it, then this gets small. Okay? So it's called the information matrix. So why is it called the information matrix? Well, because it tells you how informative your data is. Right? If it's highly informative, then it's easy to estimate. If it's not informative, then, you know, yeah, you can estimate, you can apply maximum likelihood, but actually you don't know if it's here or there or there or there because it's so flat. Okay? It's useful, you know, look, we showed here that in case of normality in the linear regression model, maximum likelihood estimation collapses to the least square estimator. So, the information matrix here, which gives me the covariance matrix here of the maximum likelihood estimator, is therefore nothing but the covariance matrix of the least square estimator. Okay? So, in case of the linear regression model under normality, this is here x prime x power minus 1 covariance matrix of the least square estimator we derive. Okay? And now think about what have this x prime x to do with the second order derivative of a likelihood function? Well, we talked about, when we discussed the least square estimator and its properties, we talked about the multicollinearity problem. So when is estimation uncertainty particularly high? When the data is highly correlated. Yeah, when it's difficult for us to differentiate between an increase of x1 and x2, and why? Because x1 and x2 look so similar. They're so highly correlated that we just have problems to differentiate. Well, that increase of y because x1 increased, or it was because x2 increased. Why? Because, you know, whenever that increases, that increases, so we cannot differentiate. This is exactly a situation which will map into high estimation uncertainty. And where do we see the correlation between x1 and x2? We see it in the matrix x prime x. Because this gives me more or less the correlation between my regressors. Okay? So the intuition of that information matrix here translates into, or has a mirror, so to say, how should I say, is compatible with the intuition we discussed and derived for the least square estimation. Okay. So, information matrix. So, in the next few slides, I want to tell you about how to do tests when we apply maximum likelihood estimation, and I'm sure that these guys here, you have heard of that, right? If you have ever run a regression or doing some statistics with some standard software package and doing some tests, then these guys here come up. Likelihood ratio test, roll test, log roll test. And in fact, all these three test principles are related to the maximum likelihood estimation principle. So they are based on likelihood functions. Right? So, in practice, very often, the results of these three test principles, you know, you have one hypothesis you want to test, and there are three ways to do it, as I will show you. And asymptotically, so if you have enough operations, right, of course, all these three tests should give you the same results, right? So otherwise, one of the tests would be just wrong, right? So, but, you know, of course, you know, this is an asymptotic result, so you have 3 different tests. So, of course, in practice, in final samples, they may give you different results, right? That hopefully does not happen, right? But it could. So be prepared. It's not a mistake in programming or something like that when something like that happens, but it could be a final sample. All right. So let us talk about the general ideas of these three test principles. Also shows you why in some applications it makes more sense to write that one than the other. So the first one is a so-called likelihood ratio test. Look here. What is that here? So it's best seen, I would say, with a graph like that one here. Suppose you have only one parameter. In general, you know, we have this general situation. We have k parameter vector unknown, or parameter vector theta consists of k unknown parameters, right? In the regression framework, it's the 1, the 2, the 3, and so on. Okay. In order to be able to draw a picture like that, just assume we have only one parameter estimate. It's a number, theta. Okay. We collect data. We write down the likelihood function, right? So what's the probability of observing our data given that theta has this value? Okay, likelihood function. And now suppose likelihood function looks like this. Wonderful, right? Maximize it. Aha. So theta hat ml, that would be the maximum likelihood estimator of theta because it maximizes likelihood. Or here the log likelihood. Okay? Cool. Now we have an estimate, I don't know, 0.5 or something like that. And now we're interested in the question, well, naturally, 0.5, could it be 0? Let's test the hypothesis that theta is actually 0. All right? So, could it be 0? 0 is here. This is a value that is related to 0. This is a value of log likelihood related to 0. And now you see that the idea of the likelihood ratio test is very, straightforward. The statistic that tells me should I reject the null hypothesis that this here is actually 0 is based on the difference between the log likelihoods. Right? Because suppose the value of that likelihood here 0 would be, say, like here. So the likelihood of my data, if I assume that theta is 0, is more or less the same as my maximum likelihood estimator suggests. Well, in that case, obviously, it is very difficult to reject the null hypothesis that theta, it could be 0, is actually 0, right? Because the likelihood is just so close. On the other way around, to make it more, suppose the likelihood of having observed my data, if theta would actually be 0, would be like here. Then obviously the likelihood is very small. So the difference between the maximized value, my maximum estimator, and the value on the null hypothesis is extreme. The decrease in likelihood is extreme. Well, this obviously speaks against the null hypothesis, right? So you see, the larger the difference here, the more drastic the decline in the log likelihood when I go from my maximum to the value under the null hypothesis, the more does that speak against the null hypothesis. Right? Gets intuition? So why it is called the log, or why it is called the likelihood ratio test? Although we take here the difference. is because of the log likelihood thing, right? So what we actually do is we compare, so we take the ratio between the likelihoods, so the maximum value divided by the value under the null hypothesis, or the other way around, it doesn't matter. But what we actually evaluate then is we take the log of it. And the log of the ratio is a difference. Right? So this is why the likelihood ratio statistic is a difference and not the ratio. Right? Because it works with the log likelihood. Okay, so here you see, this is the value here we estimate. This is the maximum value. This is the value under the null hypothesis. Of course, this is always positive because it's maximum value, right? So by assumption, this is always smaller than this one. And what you can show is that this here is asymptotically distributed chi-square. Right? This is the chi-square is always positive. Yeah? So it can't be t or normal because t and normal get negative, positive values. So obviously it cannot be normal. It's actually chi-square. And look here. Here, this figure shows you the case when we have only one parameter, and therefore, you can only have one restriction, theta 0, right? For example. But of course, in practice, we have a vector theta of k parameters, right? And we can test any restrictions, not only linear restrictions as here, right? But also nonlinear restrictions in a wall with that kind of test against the hypothesis that this restriction does not hold, right? I guess Leah told me that you practice this here for when you apply the F-test or so, right? When you have multiple restrictions on your parameter estimates on your parameter vector, right? Then you can show how these matrix are for restriction, right? Looks like. This is just a convenient way to write down. You have a set of R restrictions, 3, 4, 5, no, right? On your parameter vector. The first restriction was maybe theta 1 is 2, the second is theta 1 is 3, the theta 2 is 0, or whatever. Right? So that defines you then for each example, for each concrete example, the matrix R here defines you the restrictions. It could be 0 or any number, it doesn't matter. Alright. This is the idea. So what you see here is the likelihood ratio test uses everything. It uses the estimate, it uses the maximum likelihood estimates under the alternative, so the unrestricted model, no restrictions about theta, and it also evaluates the likelihood function under the null. Right? So you have to calculate two numbers. Two numbers of the likelihood ratio, and you compare it. Right? This is why it requires the estimate of the model under both the null and the alternative. Looks somehow natural, right? We want to compare these two values, so of course we have to calculate them. But look, there are two alternatives that avoid estimating both models. The first one is the Wolf test. And this figure here shows you the intuition of the Wolf test, which is an alternative of the likelihood ratio test. Look here. Here we have again the same figure, the same likelihood, right? Here. And right here. Okay. Likelihood ratio compares these two numbers. All right. Now suppose you don't know that number. Okay? You estimate the likelihood function, you can estimate the maximum likelihood, but for whatever reason, it is complicated to estimate the model under that restriction. So it's hard to find that value. What can you do? The idea of the wall test is, look, we already talked about that the higher the curvature here, the better for estimation uncertainty. Here you see a second likelihood function, right, with the same maximum, right? But you see, because the curvature here is higher, obviously here the value of the likelihood function for under the null hypothesis here is much smaller, right? If this here would be very flat, then this would be here. The idea of the wall test is use this information. Do not calculate this for whatever reason, because you're not able to do it or whatever, right? But estimate your maximum likelihood here, great, and then calculate the second derivative in that point. And if the second derivative is large, like here, reject. Because second derivative here large means, ooh, curvature is high. And therefore, this is expected to be small. If second derivative is, however, small, maybe like here, or it goes more drastically like there, if it's flat likelihood here, then, high uncertainty, do not reject. This is the idea of the wall test. So you see, the wall test only estimates the model under the null hypothesis. We only estimate here, and we make a guess about that value here, or that value, based on the second order derivative. Alright? So you see already, right? If it's easy to calculate both models, both likelihoods, likelihood ratio is the best. Right? However, you know, maybe it's not so easy to estimate that point. In that case, wall tests are a nice alternative. And the nice thing is that, well, asymptotically they are equivalent. Right? So if you have a lot of observations, blah, 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 then these tests is nearly as reliable as the likelihood ratio test, which uses much more estimation assumptions. So, and here again, you know, this is the typical example. We have linear restrictions, but as I said, these restrictions don't have to be linear. The formula looks a little bit different if it's not linear, but the idea is the same. So let's stick with the linear assumption here. We have a set of linear restrictions, exactly like here, right? And now look how these wall statistics look like. It looks a little bit more complicated, but it's important to see, look here, how it is, you know, somehow, how it is built, right? So first, what is this? This is the difference of the maximum likelihood estimator, the unrestricted maximum likelihood estimator, from the null hypothesis. Look here, if this is 0, then the null hypothesis is exactly fulfilled. So I estimate under the, I estimate without any restrictions about my parameters. I insert my unrestricted estimates in these restrictions functions here under the null hypothesis, right? So suppose this matrix R is like theta 1 is 0, theta 2 is 2. Okay? I estimate maximum likelihood without any restrictions, and the maximum likelihood estimate I get is 0, theta 1 is 0.01 and theta 2 is 2. So super close to the restrictions. That would imply this value is super small. This is a vector because I have several restrictions. And therefore, if you just forget this for a moment, here you have the inner product of these two deviations on the null hypothesis. restrictions are small, then this gets small. This times this gets small, because these are just the squares of that. The sum of the squares. It's the inner product of two vectors. Right? So this is a number. Right? Okay? Gets intuition? If this is large, so you see, when do we reject the null hypothesis? When the test statistic gets large. Right? When does it get large? Well, when our unrestricted estimate does not fit to the restriction. Then this is large. But that's not everything, because you learned already when we derive the test statistics for the squares or so, well, having a plausible statistic is one thing, like for example the square deviations from the null hypothesis. Yeah, the larger, that speaks against the null hypothesis. But the point is, well, we have to evaluate these numbers. We have to derive the distribution of that number. And when we go back to these squares, you know, and then all these test statistics we looked at, you know, all these coefficients and factors that are pre-multiplied on these statistics here, the only reason why we did that is because these factors helped us in order to say something about the distribution of that random variable. Because this is random, right? A random variable, random, random. So if this value is, I don't know, 1.7, the question is, yeah, well, 1.7. Is that small or is it large? Right? Ideally it should be 0, but now it's 1.7, right? Yeah, we have to say something about the distribution of that random variable. Okay? And here, this is a factor that ensures that this here, the Wahl statistic, is again asymptotically chi-square distributed. And R is the number of restrictions. So, and what you see here, the following, look here. Here you see, this here is the information matrix. So this tells me about my estimation uncertainty. So obviously, right, so the lower the estimation uncertainty, the easier is it for me to reject. Right? So I estimate a value which is rather close to the null hypothesis, looks good. Yeah, but my estimation uncertainty is super high. So it could be, yeah, I estimate a point estimate that is close to the null hypothesis, but whoa, what a high estimation uncertainty. Well, yeah, in that case, maybe I don't reject. Right? But if that is this is small, plus the estimation uncertainty is small, then I can be pretty sure. Therefore, that gets a high number, and I tend to reject. Okay? So this here tells me something about the impact of the estimation uncertainty of maximized estimation on the wall. And finally, this one here, right? This here gives me something about how much does this here changes if theta changes. This here is, you know, if that would be in general a nonlinear restriction, so some function of theta is equal to q or so, right? Then here in the general function, in that general case, here would be the first derivative of that function. Because, and this is in the linear case, the first derivative is just r. If you take the derivative with respect to theta of that here, it's just r. Okay? So this here tells me, okay, so if I plug in these values, then it's q. But what if I change a little bit the theta? Well, if I change theta, and this is still true, or more or less true, right? Then obviously, there, you know, I'm uncertain whether theta is exactly that value that equalizes this perfectly, or whether I should reject the null hypothesis. Okay? The idea is very similar to that one here. Yeah? If it tells me something about the responsiveness of my restriction. So if I insert under the null the value, so if everything is 0, for example, right, this would be, let's suppose the null hypothesis is all the parameters here are 0, right? Then the question is, well, what happens here if I slightly deviate from that null hypothesis? And that depends on the matrix R. Okay, so this is just here. These twos are just naively the numbers that give me just the numbers. How much does my unrestricted estimate deviate from the null hypothesis? Obviously, the higher these numbers, the more speaks that against the null hypothesis. This here tells me something about the estimation uncertainty. And again, make sure that you understand, the higher the estimation uncertainty, the lower W. And this here tells me something about the responsiveness of my restrictions. Okay. So we already talked about that the curvature, as you see easily, right? The curvature here affects that guy here, and this this explains why the more curvature, the more likely is a rejection of beta. So, and last slide for today. The third principle, the Lagrange multiplier. Sorry, you have a question.
It's okay. Could you please explain what is the small r? And is that simple?
The small r is just the number of restrictions. So I have 10 coefficients here, but I have only 3 restrictions on them. Maybe 3 out of them are 0. Then small r would be 3, and the dimension of theta would be 10.
I mean that small a, which is in
that
the right.
one?
Yeah, right.
This means asymptotically.
Okay.
Right? So if n goes to infinity, this statistic here converges against chi-square with r degrees of freedom.
Could that be accurate?
Would that be accurate? What do you mean with it? It's an asymptotic thing. So if n goes to infinity, the distribution, the assumption of that distribution gets better and better.
Mm-hmm. So we're near 0, so to say. We're near 0, right?
I didn't get it. Can you?
Oh, I mean that we're near the perfect state, right?
We need the perfect states?
We're near to the perfect state, right?
I don't understand what you mean.
If this term runs infinity.
This is a random variable. Yeah, because this is a random variable. So a random variable has distribution. Well, and sometimes, in some cases, we are able to derive the distribution of that random variable exactly. For example, in the least square regression model with normal distributed errors, we know the exact finite sample distribution is F statistic. Okay, here, not possible. In the very general maximum likelihood, I don't know how the distribution, it doesn't matter, right? So if I have non-normal errors, this is not normally distributed here, right? But asymptotically, I know something. It is chi-squared.
Okay.
And then it's chi-square. Look, it's not so, look here. Here we have an error term which might be normal asymptotically, and we multiply it again with its own normal distribution. So we have here, maybe we have here something squared normal, and that's chi-square.
Okay. Means
Okay?
that.
So it's not so surprising that chi-square is popping up here. Okay, let me close it. So Lagrange multiplier test. Nice thing is, this works just the other way around as the wall test. Right? In the wall test, we started here and said, we don't know what this is. Maybe let's use the second order derivative to approximate it. Here, just the other way around. In the Lagrange multiplier test statistic, we have the same setup of linear restrictions here, for example, But now we only use here the model under the null hypothesis. So look here, now we say we don't know what this is. For whatever reason, it's complicated to estimate the unrestricted model, but it's easy to estimate the model under the restriction. So here, specific example, one parameter is theta, null hypothesis theta is 0, right? And now the idea is, look, now we evaluate the likelihood function under the null hypothesis, and we do this by the score function. Look here, by the first derivative at that point. And the idea is now, look, the flatter that tangent is, the closer that value must be to the maximum value. Right? If this is super steep, then I'm obviously far away from the tangent where it's here 0. This is the optimum value. I don't know exactly where that is, but I take its first order derivative as a proxy. How close I am to that. And the closer I am, the better. So the smaller that value, right, the closer am I to the optimum. So the smaller this is, the more difficult it is to reject the Lagrange multiplier test statistic. Okay, here you see another, here you see the second factor that is important for the Lagrange multiplier statistic, because exactly as here, right? This is plausible. The smaller this is, the closer I am, the more likely is it that the restriction holds. And the same here. The smaller that is, the flatter that is, the closer I am to the unrestricted value. So small values here are good for the null hypothesis, right? But that can't be everything, because here, obviously, the estimation uncertainty does not come in, right? This is here the second order derivative. Here you see two likelihood functions which have exactly the same tangent, right? Here at that point. So these numbers would be exactly the same in these two cases, red and black, because the tangent here is exactly the same. But you see that the second order derivative here is very different. And here you see that if this is here has a high curvature, right, then I'm not able to reject, because the estimation here, I'm not able to reject because I divide by a large number, and if this is a flat thing, this is small, and therefore I might reject because it's the estimation uncertainty is small. Okay? Here you see that this score function here, the value of the score function, how I interpret it, very much depends on whether I'm in the red situation or in the black situation. Okay? The nice thing of the Lagrange multiplier test is, that it uses only the restricted model. Why it's called Lagrange? You know Lagrange from microeconomics, right? It's maximization or minimization, optimization under a restriction. This is exactly what's done here, right? We maximize the likelihood under the restriction that the null hypothesis holds. This is why it's called the Lagrange multiplier test. Sometimes score test because it depends here on the score. All right, so it's a summary of what we did here in chapter 12. Yeah, great. So we talked here about the three major testing principles in econometrics: least squares, method of moments, maximum likelihood estimation, and relating testing principles that are often applied in practice, right? There's one thing which is not on the slide which I want to mention. This wall test here, if you apply that to the univariate case when theta is just a number, right? This here boils down to the squared t statistic. So we all know the t statistic from linear regression, right? The t statistic, classic. The t statistic is nothing but the value of a Wald test. Because when we do a t-test, we estimate, the null hypothesis of a classical t-test is this parameter is 0. Right? But how do we test it when we perform a classical t-test? We estimate the model without the restriction. Right? Because we allow the parameter to be non-zero. And then we look at standard errors, blah, 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 and but you see, we test another hypothesis, the parameter is 0 or not, without having estimated the model under the restriction. We only estimate our linear regression model, where theta can be everything. So we estimate the model only without the restriction. So what we do when we run a simple linear regression and look at our t-values in order to decide whether some parameter is significant or not, what we do is we follow the Wald test principle. We only estimate the unrestricted model. And in fact, one can show from the linear regression model and the linear restriction that the Wald statistic in that special case, we have that if you have one restriction, the chi-square distribution with one degree of freedom, if you take the square root of it, it's a normal distribution. Asymptotically, that means that the t statistic is equivalent to the Wald statistic. Right? So the Wald test, although it looks a little bit weird, right? So why should I estimate the model only without the restriction? This is exactly what we do all the time when we apply t-tests. Okay? So, time is running out. Thanks for your patience. Next time we talk about Camel Lasso, and we have, how many weeks do we have? 2? I hope we have in the last week time to talk about the mock exam.